Welcome to This Explainer. You know, as a space researcher, there's absolutely nothing I love more than a good old-fashioned scientific paradigm shift. Today, we're doing a critical field debrief on a discovery that completely, and I mean unequivocally, rewrote our astrophysical models. We are talking about the very edge of everything our sun built and the legendary spacecraft that survived long enough to tell us, well, that we basically had it all wrong.
Let's just start with this astounding number, 11 billion. On November 5th, 2018, at exactly 11 billion miles away from Earth, pretty much every theoretical assumption our scientific community had about the edge of our solar system just broke down. At that unimaginable distance, a traveler crossed a threshold that changed the entire nature of its journey. It moved from an environment we actually know right into an ancient, totally unexplored medium. Now, this exact boundary totally redefines what we even call the edge of the solar system. For decades, the textbooks made us think it ended somewhere around Pluto, but no way, it doesn't. The true physical boundary is this invisible protective bubble called the heliosphere, which is constantly inflated by the sun's solar wind. And the exact edge of that bubble, the specific point where the solar wind finally runs out of gas and gets stopped by the crushing pressure of deep space, that is the heliopause.
So just how hard is it to actually reach that boundary? Well, think about Voyager 2's absolutely staggering timeline. Launched way back in August 1977, this incredibly resilient probe swung past Jupiter, Saturn, Uranus, and Neptune, and then it just kept going. For 41 years, traveling at over 40,000 kilometers per hour, it pushed outward through the solar system until it finally reached this historic threshold in late 2018.
But here's the really crucial point. Why was this 2018 crossing so much more important than when Voyager 1 crossed 6 years earlier? Well, Voyager 1 crossed the heliopause in 2012, essentially blind to plasma data. Its plasma instrument had been dead since 1980. But Voyager 2? Its 1970s-era plasma science instrument was, miraculously, still working. So for the very first time in human history, we finally had direct, real-time measurements of the plasma on both sides of that boundary.
Section 1. 5 Unexpected Discoveries Rewriting the Textbooks. What Voyager 2's functioning instrument actually sent back was a massive shock to the system. The data we received was so profoundly different from all our expectations that exactly 1 year later, 5 separate teams of my colleagues published simultaneous papers in Nature Astronomy just to explain these anomalies. We're talking about a sharp boundary, hotter plasma, a magnetic barrier, an asymmetrical heliosphere shape, and extreme galactic pressure. Let's break these down one by one.
Unpacking the first major shock here, the boundary itself. Our pre-2018 models predicted this broad, gradual transition zone, where the solar wind would thin out and slowly blend with interstellar space, kind of like two rivers merging. Instead, Voyager 2 hit a brick wall. The transition was an extraordinarily thin, sharp line. We're talking less than 0.06 astronomical units wide. The spacecraft crossed from one distinct physical environment into a completely different one in less than a single day.
Now, moving on to the second anomaly, our expectations for what actually lay on the other side were equally shattered. We had always modeled the interstellar medium as this cold, quiet, totally uniform void. But the hard data? It showed us that the plasma right outside the heliopause was measurably, significantly hotter than predicted. And it wasn't uniform at all. It was highly variable and turbulent. This supposedly quiet void was actually quite stormy.
Okay, let's dive into the third finding, the magnetic barrier. Just inside the heliopause, Voyager 2's magnetometer detected a super sharp increase in magnetic intensity. And this isn't just some random quirk in the data, it's an active physical shield. This distinct layer of elevated magnetic pressure actually impedes and deflects highly energetic cosmic rays coming from deep space before they can penetrate any deeper into our solar system.
Our fourth discovery really required comparing notes between both spacecraft. See, Voyager 1 crossed in the northern hemisphere near the nose, while Voyager 2 crossed in the southern hemisphere near the flank. Now, if our heliosphere was a perfect sphere, the boundary character should have been identical for both, but it wasn't. Voyager 2 found a thinner boundary with stronger magnetic fields, completely proving our solar system's bubble is highly asymmetric. It's compressed differently depending on which direction you look.
Which brings us to the massive punchline for the fifth finding, 10 times. Independent estimates, based on all this new data, reveal that the galactic magnetic field outside is exerting up to 10 times more pressure on our solar system than anyone had ever calculated. Honestly, the relationship between our sun's magnetic field and the galaxy's magnetic field is vastly more connected and forceful than our textbooks ever claimed.
Part 2. Shielding the inner solar system. Why this matters. So why does all this distant, deep space physics actually matter to you and me? Well, without this heliosphere deflecting those ultra-high-energy cosmic rays, the inner solar system would be a highly irradiated, incredibly hostile place, which naturally leads to a critical and, frankly, kind of unsettling question. Knowing right now that the interstellar medium is exerting 10 times more pressure on us than we thought, how stable is our cosmic shield over geological timescales? If our sun passes through a denser region of the galaxy, could that massive external pressure compress our shield enough to expose Earth to higher intensities of cosmic radiation? The absolute crucial point to understand here is this constant dynamic tug of war. On the inside, our sun goes through an 11-year cycle. When it's highly active, it pumps out way more solar wind, trying to expand the bubble. But out on the outside, you have this incredibly powerful external galactic pressure actively trying to crush the bubble inward. It's just a continuous multi-billion-mile balancing act. Yet, what's truly awe-inspiring is this final conclusion. Despite the sun's internal activity varying wildly between the Voyager 1 and Voyager 2 crossings, both probes found the edge at roughly the exact same distance, 120 astronomical units. The external galactic pressure is so dominant and so consistent that it basically holds the boundary nearly fixed, regardless of what our sun is doing internally. The galaxy presses back, and it holds the line.
Part 3. Mapping the Unknown. The final chapter.
You know, the Heliopause crossing wasn't the end of Voyager 2's mission. It was really the beginning of a brand new chapter. This incredibly resilient probe is still out there right now, actively mapping the structure of the interstellar medium point by point. But mapping the unknown comes with immense risks. In 2023, there was this terrifying communications blackout with the probe. For 14 days, Voyager 2 was moving through interstellar space, completely unable to talk to Earth. And because it never visits the same point in space twice, whatever specific interstellar conditions existed in that stretch of its journey were recorded by instruments that just couldn't transmit. 14 days of unrecoverable, totally irreplaceable data were simply lost to the void.
And honestly, that brief silence was a grim preview of the sobering reality we face today. Voyager 2 is on an unavoidable countdown. The spacecraft loses roughly 4 watts of power every single year. So year by year, the team has to make these agonizing decisions to progressively power down critical instruments just to keep the probe alive. Eventually, the power will fail completely. And when it does, the map stops forever because no replacement mission is currently designed or funded to follow it.
But wow, what a legacy it leaves behind. As NASA's Patrick Kahn perfectly stated, Voyager 2 is, quite literally, a pathfinder. Think about it. This machine, built in the 1970s, before home computers even existed, went where no one had ever gone before, and the information it sent home completely overwrote our baseline understanding of the universe. It changed every map that mattered. I want to leave you with this final, provocative thought. We now know for a fact that our textbook models were completely wrong about the edge of our solar system. So when Voyager's fading power finally gives out and the map permanently stops, what other ancient, turbulent structures are waiting out there in the dark, totally undiscovered, just past our fragile shield? Thank you so much for joining me for this explainer. Keep wondering and keep looking up.